Today's speaker is Dr. Aleks Lasek, and Aleks Lasek did his PhD at the University of Cambridge in the group of Professor Crispin Barnes, and he did it predominantly working on quantum dynamics and semiconductor structures. His PhD was numerical and theoretical, and he graduated last year, after which he moved to NIST and the University of Maryland outside Washington, D.C., where he now works as a postdoc in Dr. Nicole Younger-Halpern's newly started quantum thermal group. And we're very happy to have you here on the call, Aleks. Exciting to hear about your new results on quantum thermodynamics. So with that, thank you, and the virtual floor is yours.
Thanks, David, for the introduction. It's good to be back at the Cambridge Quantum Seminar. I should be back more often, for at least when it's under reasonable time in my town zone. Yeah. Okay, I'm going to share my screen. So hi, everyone. I wanted to present our work on experimental observation of thermalisation with non-commuting charges today. We've done it in collaboration with Rainer Blatt's group at the Institute for Quantum Optics in Innsbruck in Austria. So we're very grateful for our experimentalists. And I'm representing University of Maryland and NIST with Nicole Younger-Halpern's group. The goals of this work is to investigate how a quantum many-body system thermalizes using a quantum simulator. And a quantum simulator that I mean here is not in a software sense as we used to work with in Cambridge, but a actual experimental system. So a quantum simulator would just be some system of many quantum particles where you can engineer the interaction between them to simulate some physical problem, and then you actually measure the quantum particles to record some outcome and learn about the dynamics of the system you wanted to simulate. We want to use this quantum simulator to investigate the prediction of quantum thermodynamics. And the word quantum here mostly means non-commuting. So we're going to be working with operators that do not commute, which is sort of underlying all of quantum mechanics. And quantum thermodynamics is a rapidly developing field, and it's really exciting and interesting because real quantum systems increase in size, and we are able to do tens or maybe even hundreds of particles or qubits nowadays. And so it's important to think about the large system behavior and how they thermalize. It could be also helpful to mitigate errors in quantum computers, to investigate what effects can suppress thermalization and so suppress errors. And the question we want to answer is, are the effects of non-commutation of charges, so these quantum thermodynamical effects, actually detectable in an actual experiment? So this work is very relevant to quantum simulators. We're bridging the quantum simulator field to the subfield of non-commuting, or so quantum thermodynamics, which is just emerging since around 2016. And there's been a lot of papers published in the subfield, which some of them I'll plug in the talk. And if you're interested, just take a look at our paper that's on arXiv and look at the references. There's many papers published recently. And it's also relevant because this is the first experimental observation of the novel quantum state predicted by this quantum thermodynamics subfield. So far this field was theoretical, and we observed the first experimental evidence of its relevance. So this is the step that is interesting because it has never been done before in practice. I'll give you a little background on quantum thermodynamics for people maybe not familiar with or needing a refresher. So in regular thermodynamics, you'd usually have a standard setup where we have a small system interacting with a larger environment. So we'll illustrate with a chain of spins, or you could say qubits in this example. So let's say you have a large number of spins as a chain that interact in some way, and you pick some small amount of spins, let's say 2, to be the small system of interest, which will interact with the effective path of the large environment. And they're going to exchange charges Q between the system and environment, depending on the engineered or present interaction between them. And the word charges here just means a conserved quantity that can be exchanged. So it doesn't have to be an electric charge. Charge can be spin, energy. We could call particle number a charge. So in thermodynamics, it's just a quantity that is conserved and we can exchange between 2 subsystems. So as I said, it can be a number of things. And the system, small system S, is expected to thermalize to some thermal state rho. So as in the long time limit, we would expect the system to reach some equilibrium with the environment, which will be described by a density matrix. So of course, we have to generalize to a density matrix because of the it's effectively a decoherence process that has some classical randomness in it, because we'll be tracing the whole global system. We're going to trace the environment out to describe only the small system of interest.
I have a question here, Alex, from someone in the chat. They're asking, your environment, is it static or does it vary with time?
It does vary with time. So I guess especially in our example, it does. So in our experiment, which we'll get to in a minute, we just have a chain of ions, and they're all identical, and they all undergo the same interactions. So we can arbitrarily pick the system to be any 2 or any n, but we do 2. And so the rest will still evolve in the same way that the system evolves. We're just not going to measure them because that would be very expensive, and we're restricting to a small system. So yeah, the environment can evolve, and in our particular cases, the ions in the environment behave under the same principles as the ions in the system.
So I just got an update here in the chat. Does that mean that the thermal state can change in time?
No, because the Hamiltonian doesn't change in time. So the environment undergoes dynamics because of the Hamiltonian, but the Hamiltonian won't change in time. So the thermal state, under certain conditions, which we'll get to in a moment, we would expect to not change in time.
Okay, I think that's clear. Thanks.
So now comes the quantum part. So what happens if the charges Q do not commute? Can the system even thermalize? And why would we think that it cannot thermalize? So let's say that we set our charges to be the spin components. So the spin X, spin Y, and spin Z components. And as we know, these spin components enjoy a non-commutation relation between themselves. And just to briefly add, the energy is an extra charge that is conserved. but energy usually is always conserved, so it's sort of treated on a different footing, and it is commuting with the spin charges, but the spin charges do not commute between themselves. So in this example, we have 3 conserved charges that don't commute. So this causes this causes an effect that maybe answers more of that previous question, that the system cannot be put in an initial state that has a well-defined value for all the charges, so expectation values, because they don't commute. The system cannot be in an eigenstate of both energy and all 3 charges. It can only be in an eigenstate of one of the charges. And even then, it's such an eigenstate would also be an eigenstate of energy. So if we put the system in an eigenstate, it won't thermalize, because for thermalization, it's necessary to have multiple components in the energy expansion so that they can interact and change their relative phases. So that's one reason why the non-commutation is important. Another is just relating to the degeneracy of the Hamiltonian. So because there is no shared eigenbasis between all of the charges and energy, this creates a degeneracy in the Hamiltonian, which will also affect thermalization and makes it essentially unclear from a first look whether the system like that would be able to thermalize. So would the system like that be able to reach a well-defined long-term state or not? And here's a Nichols PRE paper that talks about that in more detail and why that thermalization might not happen. So as I said, the charges don't commute, so they don't have well-defined values simultaneously. And in classical thermodynamics, we talk about a microcanonical subspace, and that's a subspace of well-defined charges. So that's, let's say, some initial state where we set the charges to some particular values, and we can no longer do this in the quantum case because that's just impossible because of the lack of shared eigenbases. So instead, we're going to generalize it to an approximate microcanonical subspace. I might be using that abbreviation AMC here. So it's a subspace of not exactly well-defined values, but fairly well-defined values of the charges. And we're just going to define it as demanding that the variance of the charge grows at most as order of n in the total system size. So we want the variance to not increase too much so that it's relatively small, to put it in simple words. And here's Nichols' paper laying out the theory of thermalization of quantum systems that speaks more about the approximate microcanonical subspace. So we're going to put forward a so-called non-Abelian thermal state, and we're going to investigate whether the non-commuting thermodynamic system thermalizes to it or not. So it's called non-Abelian because of non-commutation, so non-Abelian algebra. And the state is going to be defined as a density matrix of 2 particles. And it's going to depend on energy and the values of the charges. And the superscript 2 in parentheses just means that it's an operator for 2 particles instead of the global operator. So it's a Hamiltonian of the 2 particles that form the system of interest, and here's the charge of the two particles that form a system of interest. It's not a square. The Z is just the partition functions that provides normalization. And beta is the so-called inverse temperature. So usually it will be just 1 over kBT. And it's a particular form of generalization of a Gibbs ensemble where we add in this extra term that accounts for our charges. That's just going to sum over the charge values times their so-called chemical potentials. But usually a common thermodynamics argument would assume that operators commute to derive such an ensemble form. So are we actually going to be able to reach it in our quantum case? And another question, what does temperature actually mean here? It's a little bit more abstract. So usually that temperature is a measure of average energy in a system, and the chemical potential is the cost of energy to add a particle into the system. Here, these meanings are a bit more abstract. So the temperature is similar to measuring in energy, but not quite, because we have this extra term here. And similarly, the chemical potential is similar to how much energy it costs to exchange a spin, but not quite. So here's another paper that talks more about deriving the non-Abelian thermal state. We're going to have to find a good initial state for our experiment that is going to be in an approximate microcanonical subspace, which is one of the requirements where we expect that at least it might be able to thermalize. And it is the initial state psi 0 that defines our beta and mu, which was the inverse temperature and the chemical potentials of the charges. So again, as a reminder, here's the form of the non-Abelian thermal state. And here it's actually the thermal state of the whole global system, which is not really tractable in practice for larger systems, but can be defined just as well. So here is the superscript tot, means it's the density matrix of the total system, so of the global system of the system of interest plus the environment. And simply we replace the operators for two particles with the global operators, that so just H and S gamma tot. And the expectation value of the energy with respect to that state being equal to the trace of the Hamiltonian times the state defines what beta is. So it's not, it's related to the expectation value of the energy. And similarly defined as the chemical potential. Now, what kind of initial state will make observing the nuts possible? So what kind of beta and mu would we actually want to have in this initial state? So firstly, it does need to be in the AMC, so approximate microcanonical subspace, which means that the values of the charges should be fairly well defined. So the variance shouldn't grow too fast with the system size. It does need to have a high expectation value of the charges because we want to make non-commutation visible. We said that this extra term in the density matrix it is proportional to the charge expectation values, and the chemical potentials, the chemical potentials of the charges are proportional to the expectation values of the charges. So if these are 0, then the form of our thermal state would not have any non-commutation effects in it. It wouldn't depend on the charges at all. So we do want to maximize them. We also want to have a inverse we want to have temperature that's not very high. Initially, I wanted to say low, but it turned out to not quite be possible to have a low temperature. But we don't want it to be at least very high, because a very high temperature will turn our thermal state into a maximally mixed state. And then we won't really be able to distinguish it from any other state. It will just be a maximally mixed state. And so why do we observe a maximally mixed state? Is it because of the coherence? Is it because of the nuts is present? It would be impossible to know. So we want at least as much distance from the maximally mixed state as possible. And we also want the state to be possible to initialize experimentally. So if it would, for example, be some highly entangled state, then experimentalists might struggle to generate it because they'll accumulate errors and decoherence during the initialization, and there won't be enough time left for the actual experiment. So we would prefer that the state doesn't have much entanglement in it. So maybe a product state satisfies these requirements. And this is something I've focused on particularly in this work. So I did an analytical and numerical search for what states satisfy these requirements. And the best candidate seems to be a product state of the eigenstates of spin in each direction. So we're going to have this subblock of the eigenstate of, let's say, Z, X, and Y spin. This is the standard arrow pointing away from you. So pointing into the page perpendicularly to the screen. So just to illustrate it, we have this small subblock of the Z, X, and Y momentum eigenstates, and then we're going to repeat it until we reach our desired system size. So mathematically, it's this pre-particle ket and then direct product over and over 3 times. So it is possible to initialize experimentally because it's just a product state. So it's not too hard to just start with some fiducial state and rotate each ion into place and start the experiment from there. It does have the highest expectation values of all charges you could have, because it's it's a product state of the eigenstates of spin. And we do want to make them equal as well, because we want to put all the charges in the same footing. For example, if we only maximize one of the charges and the other two would have 0 expectation values, then we wouldn't expect to see any non-commutation effects, because we effectively only have one charge that is relevant. And the opposite of that is, of course, having the expectation values equal across the 3 charges. And as to the particular ordering, the best, so the lowest temperature is actually reached when the like spin states are separated as much as possible. So we wouldn't want to put Z, 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 X, 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 Y, 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 because that would create a really high temperature. Instead, if we stagger them like Z, X, Y, Z, X, Y, it actually results in a not too high temperature, as I've put it. And it actually maximizes a certain benchmark quantity that is a measure of how non-commuting the state is going to be. However, the order within a subblock is arbitrary, so we could switch these around and permute within a block, and it doesn't matter. Okay, so we're going to start with this initial state and see what it thermalizes to. Let's talk about the details of our experiment. So we're working with a trapped ion simulator. As I've described, we have a system that interacts with an environment of spins. So it's a linear ion crystal of 6 to 15 ions trapped in a linear pole trap. And we're going to pick any two of them to be our system of interest that we're able to measure. And the rest are going to act as the environment. And they're going to be able to exchange energy and the free spin components between the system and the environment. So again, it's a string of calcium ions in a pole trap. And each ion encodes the qubit in the Zeeman states with different magnetic quantum numbers, which corresponds to Z plus and Z minus qubit states. And this system there's a laser in there that generates an interaction between the ions. So what kind of Hamiltonian we want to engineer with this system? We want a Heisenberg Hamiltonian because it conserves all free spin charges, which is what we want, because spin has to be conserved for it to be a thermodynamic charge. So we're just going to have an XX, YY, and ZZ interaction. And we would want more than next nearest neighbor interaction. Sorry, more than nearest neighbor interaction, because only nearest neighbor is an integrable system, which will not thermalize as well. But actually here we have an all-to-all interaction. So that's fine, the system will thermalize well and it's not integrable. So our native Hamiltonian, because of the laser interaction, has only an XX term actually, and it's a 1/r type interaction with alpha very close to 1. So it's an all-to-all interaction that drops off with distance. The actual form of the interaction doesn't really affect is not so important, in other words, but at least we would want it to be longer range than just the nearest neighbor. So what can we do with this XX interaction to engineer the Heisenberg Hamiltonian? We're going to use a trotterization scheme to rotate the system into different axes so that the XX turns into YY and ZZ. So in this picture, we can see our Hamiltonian should be trotterized to have the XX, YY, and ZZ interaction in a small time step, and then we're going to have n time steps, which is just the trotter scheme. So we can use rotations in between to turn our XX interaction into YY or ZZ. And actually a small detail is that we can actually also natively get the YY interaction, but I think it's easier to explain with just simple rotations. So a simple explanation is that we interleave the axis rotations between different steps to rotate that XX onto YY and ZZ, and that way we can generate our Heisenberg Hamiltonian. So our experimentalists, of course, use much more advanced techniques to deal with noise. We use dynamical decoupling to use different flips to suppress dephasing noise. And the actual trotter sequence is a bit more complicated. You can see that in our paper. But I think this explanation is a good illustration of the principles behind it. And another thing worth mentioning is that this simulator toolkit can be used in other experiments, and different trotter sequences could be used to generate different Hamiltonians for different needs. So it's a pretty general type of experiment. It's not just particular to what we wanted to do as theorists in this experiment. Other people could use it for other things with a different Hamiltonian generated by a different Trotter sequence. Now, what do we measure here? How do we quantify how well something thermalizes? So we can evolve our initial state under the Heisenberg Hamiltonian in our quantum simulator using this Trotter sequence. And then we can measure two of the qubits repeatedly in different bases to reconstruct their density matrix using quantum tomography for many different choices of two qubits being the system. So we can use qubit 1 and 2, 2 and 3, 3 and 4, and so on to generate different data points. Then we're going to calculate the average relative entropy to the NATs. So here's the definition of what relative entropy is. And we're using relative entropy. So we're using relative entropy because a bound on it was proved by Nicole in a previous work. So we expect that the distance between nets and other states doesn't go to 0 in relative entropy, but a useful operational definition relates to the binary testing hypothesis. So the relative entropy between two states lets us calculate the probability of distinguishing them if you're served a mixture, unknown mixture, but it contains either one state or the other state. So the relative entropy is a measure of how hard it is or how easy it is to distinguish two states if you don't know which one you've been given. And we want to distinguish whether the system thermalizes to the NATs or maybe some other thermal state, and that's why it makes sense to use the relative entropy. So as a measure of how well it thermalizes to the NATs, we'll also measure the relative entropy to two other commonly used thermal predictions. So one will be the grand canonical state, which has only one conserved spin charge and always energy. So it has a similar form, but instead of the sum over all chemical potentials and spins, it will only have the Z spin. And it's called the grand canonical because it has a very similar form to the standard grand canonical state, which would have the chemical potential times number of particles here, and is actually equivalent to it with a Jordan-Wigner transformation. As well, we're going to compare to the just the canonical state, and I should say it has no conserved spin charges, just energy is the only conserved charge. So it has a much simpler form where we eliminate this extra term from the exponent. And here is our main result in this plot. So it's the average distance of our small system of interest to different thermal predictions in time. And for this data set, we've used 12 qubits for the total system size. And then after the 12, we pick two of them and average the data over all 11 choices of the two qubits out of the 12. And they have to be next to each other. So there's 11 choices. So it's a plot of the relative entropy in units of NATs, not the non-Abelian thermal state, but it is a unit versus time in milliseconds. So this is the first recorded detailed thermalization data in time of a system like that, which is a groundbreaking result. Let's look at the data then. We have in blue the non-Abelian thermal state, relative entropy. Then we have the relative entropy to grand canonical state in orange and to canonical in green. So lower means a better prediction, because relative entropy of 0 means that the measured state is exactly the same as the thermal prediction. And we can see that for all points in time, the NAT has the lowest relative entropy to the measured state, which is what we wanted to see. And then the grand canonical is the second best, and the canonical is the worst. So we can actually see that the system that the NAT is the best prediction out of all the known predictions for a system that has three non-commuting charges. Here the inset is the theoretical simulation, and extends that time up to almost 200 milliseconds. And that's just to show that the dynamics have mostly settled by the time of the final experimental measurement, which is around there. And it doesn't drop much further than that. 50 milliseconds was about the limit that we could make good measurements in the experiment. An interesting feature is that the experimental data, which is the dots, versus the theoretical data, which is the lines, is actually dropping lower. So I'll come back to this point in a few minutes, but maybe you can think about why the real experimental data gets closer to 0 than the theoretical prediction. Because maybe we would expect, because of noise and decoherence, that the actual experiment is a little worse than the predicted theory, but here it looks to be better. So why is that? We'll talk about it in a minute.
Quick question, if I may interrupt on your previous slide. So the inset, are you using different parameters? Because the 0 to 10 range, oh no, okay, 0 to 10.
It's log scale.
Right, okay.
Yeah, it's confusing,
Okay.
maybe, but otherwise it just doesn't.
Okay, I see. Yeah,
it will just drop so quickly. It makes sense to present on a log scale.
Okay, I see. Thanks.
We've also investigated the relative entropy versus the total system size for different sizes that we did, from 6 to 15. And these are in increments of 3, because the initial state makes sense to build in increments of 3. Otherwise, it wouldn't be comparable. And again, here we see that the NATS is the best predictions for all system sizes, and we can see how it changes in total system size. We're interested to see if we would expect this distance to go to 0, as well as would the distance from the NAS to the grand canonical prediction go to 0 with system size. However, we don't really have enough data points to conclude that from this data, because we only have 4 sizes. So we tried to do a polynomial fit to this line, and this constant term would tell us, is it 0 or is it greater than 0? If it's greater than 0, that would mean that these non-commutation effects persist even in larger system sizes. But with the uncertainties, the constant we get is so small that this experiment isn't able to answer that question, and it's a question for future work. So how much is thermalisation actually inhibited by the presence of non-commuting conserved charges? I've talked before that there's reasons to believe that it would, because it causes degeneracy in the Hamiltonian, and because it makes it impossible to have a system in a microcanonical subspace, so in a subspace with well-defined charges, which are the requirements usually given for good thermalization. So we ran also a second experiment under Hamiltonian that conserves only one of the spin charges and energy. So the XX plus YY Hamiltonian only conserves the Z spin and doesn't conserve X and Y spin components, because only the total Z spin commute will be Hamiltonian. So this result in the case of one spin charge being conserved should be the best predicted by the grand canonical state we talked before. So how well? Here's the data. Similar plot to the previous one of the relative entropy versus the total system size. And we indeed see that the grand canonical is the best prediction. And the NATS is then the second best. So what we wanted to look here is how close this goes to 0 for the largest system size. So if we go back to the previous plot, we can see that for 15 qubits, the NATS went down to about 0.12 in relative entropy. And the grand canonical for its case goes to about 0.08. So it thermalizes better, it's closer to 0. So the system with 3 non-commuting charges thermalizes worse than the system with 1 charge. So it's not only that the NATS is the better prediction for the case of 3 non-commuting charges, but also that the system doesn't thermalize as well with more charges that don't commute. So we actually have an inhibition of thermalization. And now coming back to that question from the experiment, why did the observed relative entropy drop below the theoretical one? And here's a plot of the relative entropies of various predictions, as well as predictions that include some noise. So we have noise in the system, and because the noise is mostly dephasing with respect to the z-axis, because we use all of these rotations to generate our Heisenberg Hamiltonian. It's averaged over 3 directions, and it's effectively a depolarizing channel. So what happens if we add a depolarizing channel to our theoretical predictions? We do observe that the data actually drops with respect to its theoretical counterpart. So the blue dots is the relative entropy to the NATS in theory, and the orange triangles is the same, but with added depolarizing noise. So with time, it drops below its noiseless counterpart. And why is that? Because if we look at the black lines, the solid black lines, black line shows the relative entropy of the maximum mixed state to the NATS, and the dashed of the maximum mixed state to the grand canonical. So these are actually fairly low. And because the depolarizing noise brings us closer to the maximally mixed state, because it's so close to the NATS, it actually brings us closer to the NATS as well. And that's why the relative entropy to the NATS drops also. However, we can see good news here as well, which is that the NATS has much higher relative entropy to the maximum mixed state than the grand canonical state. So it's not as close to being fully random. That distance, while quite small, is not tragically small. So it's definitely observable. So that's an explanation of why that we're confused about for a little while, because it's, I think, counterintuitive that it's sort of a better result with noise than without. We also looked at pair-to-pair fluctuations in time. So here's a nice 2D plot of relative entropy on a log scale for different pairs, how they behave in time. So because the system is fairly small, we observe some pair-to-pair variation because of edge effects, where the center thermalizes better than the sides. I'm running out of time, so I'll move on. So to conclude, this is the first experimental observation of the non-Abelian thermal state, which is a novel quantum thermal state that was theorized but not experimentally explored up to now. And we have a realistic system that exhibits thermodynamics of non-commuting charges, so quantum thermodynamics, which are observable despite noise and decoherence and all the other nasty effects. We also observed that our small system of interest thermalizes less because of the presence of non-commuting charges. So the thermalization is inhibited, which is what we wanted to observe. And our experimentalists have also developed this quantum simulator toolkit that can be used in other experiments to simulate different Hamiltonians in different types of needs. So they've developed a system that has very high fidelity. They've developed a dynamical decoupling scheme that keeps the noise in check and enables us to do 15-20 milliseconds of runtime, and take measurements at different points in time, so we can have data in time of whatever you want to measure. And this reopens the door to experimentally testing this subfield of quantum thermodynamics that has remained theoretical until now. So this is the first experimental result in the subfield of non-commuting charges, which is why it's an exciting paper. And some questions for future work. Does the small system thermalize fully as n becomes large? Well, real systems are not thermodynamically large, so it's not necessarily needed for it to be interesting. But we do want to definitely answer the question whether this curve would go to zero or would it level off at a non-zero value, and also whether the non-Abelian thermal state curve would meet with the grand canonical, or would they stay separate as the system size grows. Another fine point is how much of this effect that we observed is because we had 3 charges instead of 1, so by charge multiplicity, and how much by just the non-commutation of these charges specifically. So it's something that we've already started to work on to find the corresponding systems that would have 3 non-commuting charges and 3 commuting charges. And then comparing those, we would be able to answer how much of the effects present are just by due to non-commutation. Thank you for your attention. Our paper is published on arXiv and available here. Experimental observation of thermalization with non-commuting charges. Thanks for all our collaborators and co-authors. And I'll take any questions if you have any.
Yeah, thanks a lot, Aleks, for showing your recent work and discussing it with us. Yeah, I see that Crispin already has a question. If anyone else in the participation list has,
it wasn't a question. I was just raising my hand to say hello to Aleks.
Hey, Crispin. How are you?
I arrived a little bit late to your talk. Apologies for that.
That's okay.
So I'll let other people ask the questions.
well, whilst people think about what questions they might want to ask, I wanted to ask Aleks, like, what are the main kind of benefits from this type of research project when it comes to quantum information processing for technologies? Like, is there any direct connection, or is this more foundational work that people try to figure out how to
It's
work?
quite foundational so far, but I mean, real systems thermalize, and if they're quantum, they might have non-commuting quantities that are conserved, so they would be charges. So I think it would be relevant, and it would allow us to better understand thermalization and maybe ways of suppressing errors and noise, because thermalization is like decoherence.
So is this like a future step that people want to take then to connect thermalization to quantum error correction, or
eventually it's maybe not a next step, because this is basically the first experiment on the matter, but it's a future direction that I'm thinking
Maybe
about.
to follow up on this train of thought, I guess being aware of how exactly the thermalization occurs, this is more useful for error mitigation than error correction, or do you actually see error correction being using these kinds of principles?
Well, you could engineer your system to have to be in an approximate microcanonical subspace that suppresses thermalization. I guess it would be error mitigation rather than correction. That's a good point.
Yeah. I mean, both are quite important, but yeah.
Right, I will ask a question then. So your Hamiltonian, your Heisenberg Hamiltonian, could you just flip through to it? So in terms of your results, there are no parameters in that. So, and you can add, for example, magnetic fields, and you can put in an exchange parameter, and I mean, you could even have different exchange parameters for x, y, y, and z, z. I mean,
well, then it wouldn't be a Heisenberg Hamiltonian.
Okay, right.
Right.
Well,
so we actually did that in that testing for Grant Canonical, where if so effectively this is a different coupling for the Z charge, which is 0.
Yeah.
But if you have different coupling for the Z interaction than the other two, then also only the Z charge is conserved. So it's not a Heisenberg Hamiltonian anymore. So you do want the X, Y, and Z interactions to be have the same coupling here.
Okay. And splitting the symmetry by putting in a magnetic field or something at the end of that, what does, I mean, I don't know what your criterion for this charge is. Have you got, is that written down somewhere?
Charge is just a conserved quantity. Right. So if we can put an interaction or whatever field, as long as the total spin component is conserved, that would still be a charge. Not sure what kind of field you're thinking about.
I was thinking it was like a Zeeman term, like a mu dot b term at the end of that.
Well, I think they do have that, but it's abstracted into the final Hamiltonian. So okay, the experimentalists do take these things into account. My talk is more about the theoretical part because I haven't done the details of the experiments, but they do deal with magnetic fields and make it so in the end it's the Heisenberg Hamiltonian.
I mean, it would be a natural thing to try. Yeah. Oh, very cool.
So could you say something more about this? You mentioned this kind of simulator you have with the experimentalists.
So they have this linear trap of ions, and it's a quantum simulator because kind of like we used to work with a software simulator, you can put in some Hamiltonian that you require and evolve it in time physically by just affecting this actual Hamiltonian and then measure the system at different points in time. So it's kind of like our quantum simulator, GPU accelerated software one that we used to work with that is able to time evolve a quantum system and give measurements at different points in time for some required interaction, some required Hamiltonian. And so they could instead of the Heisenberg Hamiltonian build a different one. I gave the example of the I think it's called Ising one, so just the X and the Y interactions that conserves only the Z spin, but with different Trotter schemes and maybe different ways of using the laser interaction, they could generate a whole variety of Hamiltonians that different theoretical groups maybe would want to test their predictions of some quantum many-body systems.
Right. Well, thanks so much, Aleks, for presenting. Hope to see you in person soon.
Yeah, hopefully sometime. Good to see everyone.